Good afternoon.
Good afternoon.
Today, I'd like to talk about something what is also very important. As you know, in the artificial intelligence, there are some recent trends, very popular trends. One of the most interesting in this trend is the artificial neural networks. As I told you in the previous two classes, the only thing what I can achieve, if I can achieve it during this class, to show you the real basics, to understand the relationships between the core elements. And I hope it was at least a good introduction for you. When I try to follow the recent trends in this field, I always have a reinforcement that what I believe for a long time, many, many years, it is becoming a reality. Because one way to build a powerful computer is to use the regular digital method. To use processors, memories, algorithms, and build a computer that can solve problems. Usually, this problem solving is sequential, because the original machine was sequential, starting in the 1950s. Now these days, we are learning that we have more and more parallel machines, but our thinking basically set for sequential computation. Me, or you, need to learn in the following years how to handle differently in a parallel way. Not easy to do that. It needs a special kind of mindset. One of the many metaphors within this parallel computation is the analog artificial neural networks. And as I told you several times, this is what I hardly believe. The artificial neural networks are not universal machines. They are not von Neumann or Turing machines. They are very specialized. One good example for this, if you have taken a look of this human brain, we learned about 50 years ago, there are special regions in it. And these regions are responsible for something. For example, this area here, responsible for visual processing, visual data processing, eyes projected directly to this number 17, and then the different kind of feature detections, what we learned last time, at least the word, so-called convolutional networks. The purpose of these networks is to detect features in a photo, in a picture. And based on these features, we can somehow assemble the final result, doing some kind of clustering or classification to recognize cats or recognize faces or recognize almost anything. This is one major trend. But there are many of those. If I want to list for you the most important ones, the first one is this convolutional networks, because it is so powerful these days and it is used for many areas, especially for pattern recognition, since we can find patterns on almost anything. And if the purpose of this kind of network to do pattern recognition, and it is good in it, we can utilize it. This is one big branch. But there's another big branch, so-called transformers. Kind of confusing. In this world, this new fast-pacing world, sometimes the concepts are even the concepts are, or the names are confusing. Originally, the transformers means some kind of device what can transform voltages to other voltages, or electric power with another electric power. It was a big achievement at the end of the 1800s or beginning of the 1900s to recognize the AC, the alternating current, can be transformed. Based on this very big invention, how to transform it, we were able to build electric networks for everyday use or for driving the locomotives or driving the trams or whatever is needed, or driving the computers. So one of the basic concepts related to transform was for transform electricity. But these days, there is a very, very popular and trendy area in an AI field called transformers also, the same name. It means that making some kind of neural network solution for sequential data processing, just like what it happens here in this area. This is the auditory cortex, this area here. This 41, 42, and so and the neighboring areas. These areas in a brain dedicated to process speech and language, basically speech. And then these transformers are very good to process speech, because the speech is some kind of sequential flow of data. When we tell something, it comes in words, and these words can influence the environment, the previous and the following words. And based on this metaphor, what was learned from this area here, there are some extremely powerful solutions, language processing solutions. Fantastic. If you are interested, I would encourage you to learn it. I will send you some basic literature in the readings. If you like, you will read it. So, today, I'm talking about something totally different. Just find a photo related to this topic. When they analyzed how we process the information in our brain, our head, using some new technologies, we can identify where the areas are working. For example, when the person was asked to read something and think about it and tell what he read, what he was reading, first the visual cortex was activated, and then the frontal cortex was activated to think about what was that, and finally this language area was activated. And it was in a sequential row, if the person was asked to do this in sequential. So it was relatively easy to identify. It is fascinating, and I'm almost positive that in the following years you will learn a lot in this area, because this is the biggest trend in this field. Today I'm talking about something else, totally different. It will be the search methods. The search is one of the basic area in computer science. The reason? Because in most real-life situations, we don't have equations. As I told you last time, if you have equation for some given problem, don't waste time to do artificial neural networks or anything else. Use the equation, plug the data in it, and calculate it, and that's it. Unfortunately, in most real-life situations, we don't have equations. We have experimental data, a lot of data. We live in a data age these days. And based on the data, we can do something, for example, using neural networks. But if we have data, but we don't know the optimal solution for some given problem, what can we do? We need to find it. How to do it? Using some search. Because of this, in the last 50 years, the search area grown huge. There are many search methods, many search methods. One of them is better than the other one, and also it is important to know the search usually not universal. If we have some specific problem, we need to have a specific search for that, dedicated for the specific task. My goal, the lecture today, with my lecture today, to give you some idea how to connect the elements, what is the relationship between the basic concepts. I don't have time to tell you all of the basic or most important search methods. I picked some of those. The reason why I picked those because I can show you the basic concept behind it. And then if you will understand the relationships, you can base on it in your future. Everything will change very fast, but some basic group of problems will remain. For example, search. We need to search as long as we will live. We need to search something optimal. And if you don't have equations, we need to do something else. This is what I like to tell you today. Just, I hope you will be interested to listen to these basic methods. The second part of the class is even much more interesting. For me, it was extremely important and very interesting when I learned it at the beginning, for the first time. The nature uses some very special search methods to search the optimal. For what? For the surviving. And how the creature can survive on Earth. And we have a pretty good, not finished, just a first step of understanding how does it work. It is called genetic algorithms. And we can use it in technology, and we can do many things with it. Already, even our knowledge is very limited. We are just at the beginning stage in this field. And in the following decades, probably we'll see a huge change also in it, because the genetics is one of the big areas in science. And we learn more and more how the genetic code influence life. And then in parallel of this, we will learn how to handle the genetic operators. And we can mimic it in technology, just like building computers based on the brain. We can build specific search based on the genetic procedures, what we learn. Fantastic, very fascinating. So, if we are talking about search, one of the simplest ways to represent the situation using graphs, meaning that we have many variables, and then these variables can influence something. And then this result of this influence, we have a specific stage. We have a specific situation. And we can represent the situation as a node, something like this specific situation where we are, based on the given variables. And then if we will evaluate the stage where we are, we can tell it is optimum or not. If it is optimum, we feel happy with it, we don't need to do anything. We can be just lazy and just wait, that's it. But in most cases, we are curious to find something better, or we know definitely it is not optimal. What can we do? Try to find some other situation based on the variables, because if we will change the variables a little bit, we will find some different inputs. This different input can take us to the different stage. And then this kind of thinking can be represented as a graph. It is a very special group in math, the graph theory. There's a long history of it. If you're interested, you can find something fascinating. But tell you just the very basic ones. We have nodes, these points here, and we have so-called edges, these kind of connections. Meaning that if we are in this given stage, using a specific operator, we can somehow change this stage. So for example, we can go from this S to the B, or we can go to S to the A, using a different operator. One operator will take us here, another operator will take us there. Clear? And the goal is here to find the optimum. It can be a goal, when we are happy with it. But the problem, usually, this is somehow deep, because we cannot jump right away from here. It would be a very lucky situation if we are not happy with the situation. We change one variable, just step one, and then we are there. It is not a very likely situation. We need to take several steps, because the optimal is somewhere deep, somewhere far away. And we cannot step right away there, because we don't have a specific operator to take us from here to here. Just some kind of intermediate operators what can take us from one stage to another one. And this is the situation. And then we can walk from here, going this way or going that way, and finally, if we are so lucky to reach this position, this so-called goal position, we can be happy with it. And then, this is two basic kind of trees or graphs. One is the so-called tree, when there are just branches, there are no loops in it. Another big category is when we have loops, for example, this one here. There's one loop, another loop, something like that. So in worst case, we can go like this in a circle. It would be a kind of dumb thing to do it. Not to do it, we need to have some memory, to remember where we've been before. Because if we cannot have some memory, we have a new situation, we don't like it, we see what can we do, we will choose something and go over there. And if you don't remember we already been there, it's a problem. So you need to have some specific memory, and I will show you what is the two basic memory type for this. The last in, first out, the LIFO, and the first in, first out, the FIFO kind of method. So in these days, this kind of graph representation is extremely popular and extremely important. As important as a computer itself. Because we learned the whole world is connected because of the internet, and everything influences everything. And based on this very basic recognition that everything is connected, this metaphor can be utilized for many, many areas. Human connections and any field can be represented basically using a graph theory, graph representation. Analyzing this graph, we can draw conclusions, very important conclusions, and there's a new science called network science. Based on this network science, we can predict things because we have a huge amount of data. Based on those data, we can see how those data are moving, in what direction they are moving. Based on this movement, we can predict the future. Unbelievable, fantastic. One of the key persons in this field, Hungarian one, if you're interested, I would encourage you to read something from him. Extremely interesting person. His name is Albert László Barabási. He's an extremely well-recognized researcher in the field, very influential, working for Harvard, working for big universities in the US, same time working in Hungary too, and he published many, many fascinating books about this area. I would encourage you to go to the library, get a book from him, and read it, and you will think differently if you will have this reading in your head. So the problem with the search, usually it can be a huge space what we need to search for. And the search can be extremely tiring and extremely costly and takes a long time. And to be able to understand the complexity of this thing, I'd like to show you a very basic example in this field, the so-called traveling salesman problem. Maybe you already heard about it. And if you are so fortunate to work a company parallel to the school, as I think many of you are doing at the same time, to getting some income and support yourself, your boss can come to you and say, are you studying at the Neumann faculty? Yes. Are you studying programming? Sure. Can you do some favor for me? I have a very simple problem. I have a delivery company. I have to deliver packages. It's one of the very popular jobs today, to deliver pizza, deliver packages. And the task is the following, what I need to solve. I have many packages, what I need to deliver for the person who ordered it. And the person who is carrying this package needs to do it optimally, using a fewer time or the minimum time or minimum gasoline or minimum energy driving a bicycle. We need to tell where to go, because that person can have a list where to go. Those are those destinations. And if we can help him to follow the optimal path, how to go from one to B and B to C or something like that, it would be a great help for him. Can you do it for me? Probably, if you are not familiar with this topic, you would say, sure. It's such a very easy task. I will calculate the distance between the different destinations and add them together and figure out if I would go this way from A to B, B to C, something like that, it will be this long. And if I try a different path, it will be another path. And when I will calculate it also, since I have a very powerful machine on my desk, I can do it in microseconds. I can order it and pick the best ones, the shortest ones. And then give the list for the guy who is riding a bicycle, if he's a bicycle rider, and then he can deliver the stuff. Easy, isn't it? To write this kind of code is the problem. Very easy to do it. If you are a good programmer using any languages, computer languages, you can write this code within hours, or maybe less than hours. So, but the problem is the situation. If there are some basic requirements, for example, this one, visit each destination, in this case cities, only once. And the second, you need to visit all of them, not just some of them, the most important, who will give a biggest tip for you. They need to deliver to everyone, all of the destinations, but only once. It's easy, isn't it? Simple. But the problem is the following. If here is the representation of this problem, the problem is the following. If we have 10 destinations, the different kind of solution can be 181,000. If we have 20 destinations, 20 points to deliver the thing, the different path can be this number, 10 to the 16th different kind of path can be calculated. And if you have 30 cities, totally hopeless. There is no such computation power on Earth in the whole universe what can calculate for you this kind of situation. Even the problem is extremely simple. And this kind of problem called NP-complete. NP-complete. You need to remember if you don't know what is that. It's a very specific group of problems. These are the hopeless problems, but there's no way to solve it. The real problem, that is not easy to recognize what are those NP-complete problems. If you know this kind of traveling salesman problem is one of them, and if you will get a job or task to do something similar, you can tell, wait a minute, I can do something for you. You can tell to your boss, but I cannot do the best one. And why? Because this is the computational intense and hopeless problem to solve using any technology these days. So this is a situation. This problem called combinatorial explosion, because the way how the variables are growing, The number of solutions can grow exponentially or can be factorially. It's a problem, there is no way to solve it. Question, what can we do? Because somebody had to deliver those packages. We need to do some approximation. I will show you how to do that, for example. It is not 100% good, but close to good. And close is enough. Better than doing nothing. Just try randomly and do something from heart. So this is the list of the different kind of problem categories. You need to know it. I will ask it in a test. Remember. For example, the most simple problems are so-called polynomial problems. We can have many variables, we can have a complicated function to describe the problem. But if we have a problem, if we have a polynomial description function for that, we can calculate it. Having any fast computer, we can calculate it in seconds, milliseconds. No problem. This is called the so-called P problems, polynomial, because the equation can be even polynomial. The second category is the NP polynomial, so-called hard problems. We can have an efficient algorithm to calculate somehow, but it is not a sure thing. Likely we have a good solution, almost optimal solution, but not 100%. We are not 100% sure in it. And the third category is the so-called NP complete, but it's impossible to solve optimally because of this explosion, the exponential situation here. The real problem is here, it looks something like that. Sometimes we cannot differentiate between NP and NP complete because we don't have a deep knowledge what kind of problem is that. We don't have equation. If we have equation, we see the variables and in a squares or in a power, we can tell it is exponential function. But we don't have equation. That's a problem. So we need to have some estimations, and we try to do our best, but we cannot be sure it will be 100% optimal. And I will show you soon the very important concept, locally optimal or globally optimal. Very important to know the difference. In most cases, we don't have a chance to have a global optimum, just a local one. What is approximately okay, we can be very happy with it. Unfortunately, we cannot check what will be the real optimal. And there are most life problems are something like that. So there is a long list of well-known NP complete problems. I made just a short list from here. If you are interested, you can easily search for NP complete problems on the internet, and you can understand those. You can build up some kind of pattern base in your head to recognize those kind of situations. And if you see that kind of movement, you can tell, wait a minute, we need to have a specific method to handle it. And any specific method can give us a 100% good solution, just approximately good solution. So there are a list of very basic concepts what I like to tell you very briefly. First is the so-called global optima, meaning that the very best situation what I can imagine. If we don't have any limitations, computational limitations, we would be able to try all of the alternatives and pick the best one. We can tell this is the global optimum, the very best one, what can ever happen. As I mentioned many times already, sometimes we don't have this luxury to have it because we don't have enough computation power. And anyway, it is hopeless to do it. So another area, another concept here is the local optima, what is more or less okay, but not 100% okay. Just give you an example of what you already know. Using neural networks, one of the main goals is to find a given weight structure. Because we set up the network, the topology, we connect with weights, and if we are lucky to set it right, this kind of neural network can do a good classification, good mapping between two functions, input function and output function. But the problem, we don't know what kind of weights we need to set for that. That's why the learning will come in picture. So we need to somehow train the network, modify the weights. And in order to do that, we learned the back arrow propagation method last time. Meaning that if we have an error function, we can define what the error is. Then we use some kind of analytical method, some math, to calculate the derivatives of the function in a given weight situation. Based on these derivatives, the slope of the error function, we can decrease it, somehow change a little bit the weight in order to get better result. But unfortunately, as we learned last time, if the function is something like that, we have some kind of inflection points in it. When the derivatives are 0, we cannot change anything in a weight, and still we are not good in it. That's why we can stuck. The derivatives, if the function derivative can be 0, we can stuck. That's why it's a problem. We can have a local optima. It is okay among most of this situation what we tried. This is the best ever for us, but not for the whole situation. Because if we would have a chance to try another one, we can have a better solution. I will show you some other examples what will be clear for you. In mathematical terms, we can use these operators. Using these operators, we can change the stage or the state of the search space. There are several methods. The major groups are, first one is the trial and error. If we don't have any idea how to do it, we are not happy with it, what we have, we can try something else. This is called the very first one, the trial and error method. It is called non-informed search. We don't have any information. We will choose another variable, change it, plug it in, calculate it, and check it is good or not. If it is better than the previous one, we are happy with it. But if we are still not very happy with it, we can try another one, so on. This is the trial and error. And there are some other informed methods too, when we can, for example, consider the cost of the search, not just a goal, how much it will cost for us to do this search, and we can decide, worth it or not. If not, maybe what we have it is good enough. But if it is not too expensive to go to another stage, making another step, we can try it. And if we are lucky, we can get better result. So, and finally, there is a huge group called Heuristic Search. I put here the heuristic, what is that? Is something very important idea, because in most situations we can use heuristic to solve problems. And then, two basic concepts what I like to just mention here. There are two very useful lists. It is so-called open list, where we can register the situations or the variables where we've already been, the stage where we've been. Because if we step to the next one, before we're doing this step, we can check, have we visited already the place or not? If we did, it is not worth to go there. This is the open list. We already checked it. Or the closed list, where we already finished that. We already evaluated that point, and then we don't need to go there. You will see more clearly soon when I will show you the graph. So this is the general method. It is called production system or called search method. It is a general algorithm, very easy to understand. First, we need to select the initial stage where we are, and then evaluate it. If it is not in a goal, it doesn't show us a goal, we need to begin the search. We will search one operator, but we change the situation from one stage to another one. And then we need to do it as long as we will reach the goal. So as you will see this loop here, this loop will go as long as this goal will be not met. If we are at the goal, that's it. If not, we need to keep doing that as long as it's needed. So this is the basic algorithm. And then one of the very first and very influential method was the so-called depth-first method. Very easy to understand, especially if you will see this graph. First, we are in this starting stage here. And then we have two operators. We can choose this one first, and we can go to A. And then if we are at A point, we have two operators again. Then we can go to C, and then we can go to D. And then this is the so-called open list, what I mentioned just minutes ago. If we are this is the list what we record where we are, what we visited, what we opened for evaluation. First we open the S, we put it on this list. We will check the S, and it is not good for us. We need to keep doing this. So we need to go deeper somehow in this graph. Then we will go to S, A first, starting, for example, in this direction. We will put this A first, and then we check another option to B. This, we will put it here. And we always check the top ones. This is here. So we will check the A. If it is A is not good enough, instead of checking the B right away, we will go deeper. We will go to C first, and then we will go D first. And then we will check what is on the top of this list. We will check the C, and if C is not good enough, there is still something on this, and on this list. We cannot go further from the C, so we need to check the D. And if D is not good enough, we need to check B. If B is not good enough, we can go from B to E and F. That's why we are putting this B, E, and F here on this list. And then if we are checking E, it is not good enough. Then we have still something at the F on our list. We will check the F. And then, as you will see, when we check the E, instead of checking F right away, we can extend, or we can go to G, and then cannot go further with G. We will go to goal, and we will stop there. Please raise your hand if you understand this very simple thing. Thank you very much. Very simple. This is called the open list. Since it is a tree, we don't need to have the closed list, because we cannot go again in the same loop, because if we checked already one element, one stage in it, it is done. But we have a loop in it. We need to have a so-called closed list, what will list us where we visited before. Clear? This structure called last in, first out. Last in, first out. It's a very basic structure in computer science, because we don't need to have addressing. We have a specific place to put things, specific place to get something. If you have something what to store, put it on the specific space and just push it down. It is just like a sack. It is usually called as a stack. Putting on the top of this thing and already getting something on top of the stack. Clear? Very important thing in computer science. It is used very often for search. Here is the algorithm. Very easy to understand. Since you are studying this field, not just watching that, you can read this algorithm very easily, starting with the first node, the start point, and then we will have a loop. And in the loop, we are going to use the first operator, and then we will check it is good or not. And then if it is not good enough, then we can keep doing that as long as we will reach the goal. I hope it is clear for you. It is a little extended version of this basic algorithm what I just showed you a second ago. Clear? So something like this. In a test, since we are in a school and need to give a test, what is not my favorite part, you will have this kind of situation in a test. I will give you something like that, and I will ask you to figure out what is missing, for example, here. I will give you this list, and I will ask you what is missing from here, using the specific depth first search. If you understand the concept, what is easy to do that, but need to learn it. And if you understand it, you can figure out what is missing here, and that's it. If not, you can guess something, but not easy to guess. Clear? And then, please follow this example at home. I don't want to tell you right now. Please check it. If you understand, you can have another. I give you some test problems for in this presentation. Please do the test. Please fill it out. And then, if you will see it in the test, there will be no problem to solve it. If not, it will be a problem. If you have a graph, meaning that there is a loop in it, there is some extra element in it, we need to have a closed list too, not just the open list. We need to have a closed list, because if you already visited one of the points, we need to remember for that. And instead of coming from the different direction, we would go there, we need to check if it is on a closed list or not. Because it is there, we don't go there anymore. Clear? This is also a list, what I would encourage you to understand, and hopefully it will be easy to do the test for you. The second very important basic method is so-called breadth first, where we are not going deep in a tree, rather horizontally. To do it horizontally, we need to have a different data structure. It is called first in, first out. It is a pipeline. The real advantage to have this kind of data structure, we don't need to have addressing. We don't need where to put it in a pipeline, put it into the end of the pipeline, and always get something from the end of the pipeline. This kind of very basic data structure can help us to go, instead of deep, we will go horizontally. First we will go this way, and then we will go this way, and then we will go this way. You can have a question, and what method we need to choose? No easy answer for that. If we have some idea what kind of data structure can describe our situation, if it is a very deep structure, we need to use the depth-first search. But if it is horizontal, so many variables, and each variable can give us a good solution, we rather can try this method, this kind of horizontal or breadth-first method. To understand the situation, this list can be followed easily, starting with the S here, and checking the S. If S is not optimal, we can go to A and we can go to B, and then before we will go further, we will check A. If A is not good enough, then we will check the B. If the B is not good enough, we will upload these two variables at the end of the pipeline. This is that. We are putting this at the end and getting it from the top. And going step by step on this, we can finally go to the goal. This is sorry for this Hungarian words in it. This is the goal here. And then if the graph is, or the tree is horizontal, we need to use this breadth first, the horizontal search. If not, we need to do something different. If we have a graph, the situation is the same, but we need to have a closed list too. And here is the closed list. And I will encourage you also to do it at home. You can do it by yourself easily if you understand the basic concept, but I'm sure you do. There is another important element when we calculate the minimum expense, not just a situation. We will calculate how much it costs for us, meaning that these edges here has a value or cost. Before we take one of the steps, we will consider it is worth it or not. And we choose always the cheapest one, the smallest one. These are numbers, and these numbers can represent the value or the cost of the search. We will go always the cheapest path. It is an obvious solution for us, isn't it? We like to be optimal. We like to be very we don't want to spend too much money for that. We are choosing always the cheapest one. To follow this, very easy. First, we will start with the S, putting on this list. And this is the cost here in the brackets to show what was the cost to go there. It was 0. And then we check the S. And then on this open list, we will put the B and we will put the A, these two elements here. But in the same time, we are recording that which direction we were coming, because it is good to know what is the path what we followed. This subtitles here shows the direction. It's coming from the S, it is coming from the S also. And the cost to go to B, it is 1. The cost to go to A, it is 4. And instead of going forward, this is the key element here, we need to order this list. Find the smallest one, if we want to follow the cheapest path. And then, based on this list, this ordering, we can pick what was on the top. This was the cheapest one. And then, from the B one, we can go to E and F. The cost to go to F would be 4. The cost to go to E would be 3. And then, if it is on a list, then we are going to order it again, and we will pick the cheapest one again. What is the major difference between this one and the previous one? There is an ordering step between that. Ordering using these values or the cost of the elements. Clear? We are always choosing the best ones, what was cheapest for us. It is something very important. And finally, we can go deep enough, but if you don't have any clue where the goal is, what situation is the optimal situation, it is not a sure thing we will find it efficiently. There is another example for doing the searching graph. Instead of having only an open list, we need to have a closed list too. The reason why I'm telling this is pre-open list, because the pre-open list is what we get from listing the elements, the potential elements, and the real open list when we order it. And to do this ordering, this is the order list, we will put the cheapest one on the top, always here, and always picking the cheapest ones. This is the example for you to practice. I encourage you to do it at home. Try to find what are the steps for reaching the goal 1 or goal 2, and this kind of problem will be in a test, I can tell you. Go back for one step for the heuristics. The heuristics is something like that. The heuristics, it is a solution based on our previous experiences. Having some great idea, it is some kind of bias, what can help us to do optimal or close optimal solutions. The original word came from Archimedes, this eureka, I found it. And then if we have some idea how to solve some problem, what kind of solution we will have, what can lead us to the goal, we will try it. And if we are lucky, we have better than before. It happens very often. For example, using for the traveling salesman problem, this kind of idea, one good method could be, before going to the next city or next point, we will look around and check which one is the closest one. Then we will go to the closest one. And if we are there, instead of choosing randomly the next destination, we will look around again and check which one is the closest one. And always doing the best steps. We can tell we are doing optimal because we are doing the best decision. We are doing the best decision in any situations. Unfortunately, it cannot be globally optimal. It can be locally optimal. It can be approximately good solution, but if we would have a chance to list all of the potential paths, sometimes it would be good to go farther and then come back from there, but we cannot check it because there are usually so many different solutions for the problem. Using this very simple logistic, very simple idea, heuristics, we can shrink the search space significantly. Originally, it was the equation for describing the situation. This, and there was a factorial in it. Because of this factorial, it grown extremely fast. That's why we have this 10 to the 30th different steps. Using this very simple heuristics, the number of different solutions could be n squared. It's a major difference. We can do it in microseconds. We are using computers. And then if your boss would approach you, do this optimization for me, say, sure, I will do it in 2 seconds or 2 minutes. We will do choosing the best ones always, and based on this very simple idea, you can provide a good list of steps for the driver. Clear? But the problem is the following. Sometimes we have a very complicated situation, something like that. Unfortunately, we don't have a clue sometimes how the search space looks like. We can evaluate the situation where we are, but we cannot tell it is how far from the optimal. And then we need to do some search, do what can we do, and then we will follow the steps. Let me tell you before the break, let me tell you a very simple example. If you like mountain climbing, if you want to go up on a high mountain, and then you will decide next day you will go up to the peak. It is fun, beautiful, interesting to see things around from there. And next morning when you woke up, you notice that there's a huge fog everywhere. You cannot see anything, even your nose. You can see maybe your knees or something like that, but you cannot see the situation. And you cannot postpone your hiking trip for next day because you need to do that day. What you can do? What can you do? Go regardless of the weather, hoping that maybe in the middle of the day it will be sunny and then you will enjoy the scenery. But not at the beginning because it's a huge fog everywhere. What kind of idea, what kind of heuristics you can use to do something good? Very easy to answer. You need to go up always. When you go to the mountain, you will go to the hill, you will see where is the slope is, you will go upwards. Because your goal is to go up on the top of the hill. And if you are going always upwards, no problem, because you are doing your best. And you are doing that for the whole day. Going up gradually, higher and higher and higher. Enjoying the good air, but not to see anything. And eventually you will reach a point where there is no further up, because there is no further up steps. You are on the top of the hill. You will stop and wait for the sun. And the sun will come maybe soon, and you will look around and you will see all of the other peaks are higher than you are. Many, many other peaks everywhere, a lot of people on it. You are stuck in this position and you can just look, oh my God, what wrong did I do? Nothing. You did your best. You followed this very basic heuristics to go upwards always. And I hope it is clear for you, this is the same thing in neural network training, and same thing in many, many areas when it is called gradient method. This gradient method is one of the big heuristics. You're going upwards always, or going downwards always, minimizing or optimizing, going upwards. What can you do then? You cannot jump from here to another peak. You're not good enough to do that. You need to go down and start it over. If there is a fog again, the next day you are unlucky. But if we try somewhere else, go far away from that position where you started yesterday, you have a chance to go maybe a different peak. Since you don't have a record where to go and how to go, it's a problem. And the problem is here, what I will talk to you soon in the next lecture, what the nature does in this situation. First, they will use not a single search method, they use parallel search. Use many, many mountain climbers to find the peak. This is one of the elements. This is what nature does. We need to have a population. We need to have many elements in the search situation to test the situations and optimize it. But there's another very important element in it. We need to have a way to how to combine the previous knowledge, the previous experience. We need to somehow record it or have some kind of bookkeeping, what was good or what was not. And we need to have some method how to combine this knowledge. This is what nature does. I ask you to have 5 minutes break, and after that I'd like to tell you how the genetic algorithm works. Thank you.